This episode is proudly sponsored by the globin chains, the star-crossed lovers of hemoglobin. Picture, if you will, the alpha and beta globin chains, destined to pair up perfectly and form the magnificent hemoglobin molecule. In the whimsical yet tragic world of thalassemia, a cosmic genetic mix-up means there's either too many alphas for the betas or vice versa. The lonely, unmatched chains, unable to find their perfect partner, become agitated and unstable, causing a microscopic drama of imbalance that fundamentally compromises the very heart of the red blood cell.
Welcome back to The Deep Dive, the podcast where we connect the dots from the molecular level right to the microscope stage.
It's great to be back. Over the last 2 episodes, we've tackled the 2 titans of anemia that revolve around iron. We started with the undisputed champion, iron deficiency anemia, a straightforward problem of supply. Then we unmasked its great pretender, anemia of chronic disease, which is a problem of access, with iron locked away by hepcidin.
Exactly. In both cases, the central issue was getting iron to the erythroblast to make heme. But today we're completing the trifecta of common microcytic anemias by looking at a condition where iron is not the problem at all. The iron supply is fine, the access is fine, but the red cell factory is working from a faulty genetic blueprint.
You've set that up perfectly. Today, we're diving into the thalassemia syndromes. This is a production problem of a completely different flavor. It's not a lack of raw materials. It's an inherited, quantitative defect in the protein portion of hemoglobin. And understanding this fundamental difference is the key to unlocking a lab pattern that can look similar to iron deficiency at first glance, but has some fascinating and unique clues of its own.
And that's our mission today. We're going to build the story from the ground up. We'll start with the globin genes themselves, then explore the 2 main pathophysiologic consequences of a thalassemic defect, and finally, we will connect that pathophysiology test by test, explaining why the RDW is often normal, why the RBC count is paradoxically high, and what's really going on when you see a smear loaded with target cells and basophilic stippling.
It's a journey from a DNA sequence all the way to a hemoglobin electrophoresis printout. Let's get started. To understand a faulty blueprint, we first need to look at the normal blueprint for our main adult hemoglobin, hemoglobin A.
Right. Hemoglobin is a tetramer. It has 4 components, 2 parts heme and 2 parts globin. The heme group, with its iron atom, is what binds oxygen. The globin chains are the protein scaffolding that surrounds and protects the heme. For adult hemoglobin A, which makes up about 97% of our hemoglobin, that scaffolding consists of 2 alpha globin chains and 2 beta globin chains.
And the most critical concept in normal hemoglobin synthesis is balance. The body produces alpha chains and beta chains in almost a perfect 1-to-1 ratio. For every alpha chain made, a beta chain is made to pair with it. This exquisite balance is essential for a stable, functional hemoglobin molecule. Thalassemia at its core is the disruption of this balance.
So thalassemia is defined as a genetic disorder characterized by a reduced rate of synthesis or a complete lack of synthesis of one or more of these globin chains. It's a quantitative defect. The chains that are produced are perfectly normal in their structure. There's just not enough of them. This is a key distinction from hemoglobinopathies like sickle cell, where the problem is a qualitative one, a structurally abnormal chain.
A crucial distinction. And because we have alpha chains and beta chains, the thalassemias are broadly divided into 2 main categories: alpha thalassemia, caused by deficient alpha chain production, and beta thalassemia, caused by deficient beta chain production. The genetics are a little different. For alpha chains, we have 4 genes on 2 on each chromosome 16. For beta chains, we only have 2 genes, 1 on each chromosome 11. This difference in gene number explains the wide spectrum of clinical severity that we see.
Let's use beta thalassemia as our primary example because the pathophysiology is so classic. So imagine a patient with beta thalassemia trait, also called beta thal minor. They have 1 faulty beta globin gene and 1 normal one. What are the consequences inside the red cell precursors in the bone marrow?
There are two fundamental problems that happen simultaneously, and they explain everything we see on the lab. The first problem is straightforward: underhemoglobinization. Because you're not making enough beta chains, you can't make enough normal hemoglobin A. The erythroblast divides, but it doesn't get filled with the proper amount of hemoglobin.
And just like we saw in IDA, when there's not enough hemoglobin to plump up the cell comes out of the factory smaller and paler than normal. This directly causes the microcytosis, low MCV, and hypochromia, low MCH and MCHC, that puts thalassemia on the differential in the first place.
Exactly. But that's only half the story. The second problem is, in many ways, the more destructive one. Remember that 1-to-1 balance? In beta thalassemia, the alpha chain genes are perfectly fine, so the cell continues to churn out a normal amount of alpha chains. But with a shortage of beta chains to pair with, you now have a massive excess of unpaired alpha chains floating around inside the cell.
They're like a dance partner without a partner. What did these lonely alpha chains do?
They do terrible things. Unpaired alpha chains are highly unstable and insoluble. They precipitate inside the red cell precursor and form toxic inclusions. These inclusions damage the cell's internal structures and its membrane. This leads to the central defining process of severe thalassemia, ineffective erythropoiesis.
Let's unpack that term. Erythropoiesis is red cell production. Ineffective means the process is happening, but it's not resulting in viable cells.
Precisely. The bone marrow sees the anemia and goes into overdrive. It becomes massively hypercellular, trying to pump out red cells. But the majority of the erythroblasts it produces are so damaged by these precipitated alpha chains that they're recognized as defective by macrophages right there inside the bone marrow and are destroyed before they ever have a chance to enter the circulation. The factory is working at 200% capacity, but most of the products are thrown in the trash before they leave the building.
And in the most severe forms of beta thalassemia major, this ineffective erythropoiesis is so profound that the bone marrow expands dramatically to try and keep up, leading to the bone deformities and chipmunk facies that are classically described. But what about the cells that do manage to survive and escape the marrow? They're not exactly healthy, are they?
Not at all. The few cells that make it into the bloodstream are still carrying these precipitated alpha chain inclusions. The spleen, with its army of macrophages, acts as the body's quality control filter. As these damaged red cells try to squeeze through the splenic sinusoids, the macrophages bite out these inclusions. This pitting process damages the cell's membrane, reducing the cell's lifespan and leading to a hemolytic component to the anemia. It also creates the wild variations in shape, the poikilocytosis, we see on the smear.
This is a perfect bridge to the laboratory bench. We have this picture of underhemoglobinized cells and ineffective erythropoiesis. Let's start with the complete blood count for a patient with the common beta thalassemia trait.
You'll see a mild anemia, so the hemoglobin and hematocrit will be slightly low. You'll then look at the indices and see a dramatically low MCV, often in the 60s, and a low MCH and MCHC. So far, it looks a lot like iron deficiency.
But then you look at two other parameters that scream thalassemia. The first is the RDW, the red cell distribution width. In classic IDA, the RDW is high because of that mix of old normal cells and new microcytic cells. What about thalassemia trait?
The RDW in thalassemia trait is characteristically normal or only slightly elevated. This is a hugely important differential clue. The genetic defect is present from birth. Every single red cell the factory produces is made from the same faulty blueprint. So while they are all small, they are all uniformly small. The analyzer sees a homogeneous population of microcytes and spits out a normal RDW. A very low MCV with a normal RDW is classic for thalassemia trait.
Okay, that's clue number one. What's the second massive clue on the CBC?
The red blood cell count itself. In IDA, the marrow is starved of a raw material, so production sputters, and the RBC count is low. In thalassemia trait, the body tries to compensate for the poor quality of its red cells, low hemoglobin content, by cranking up the quantity. The bone marrow, despite its inefficiency, just pumps out a massive number of these tiny cells. So you often see a normal or even an elevated RBC count, over 5 million.
So you have this paradoxical picture of anemia with a high red cell count. This combination of a low MCV and a high RBC count is so classic that several mathematical indices have been developed based on it. The most famous is the Menser index.
The Menser index is simply the MCV divided by the RBC count. If the result is less than 13, it's highly suggestive of thalassemia trait. If it's greater than 13, it points more towards iron deficiency. For example, a patient with an MCV of 60 and an RBC count of 5.5 has an index of 10.9. Think thalassemia. A patient with an MCV of 70 and an RBC count of 3.5 has an index of 20. Think iron deficiency. It's a great little mental shortcut for the MLS.
Absolutely. Now let's move to the peripheral blood smear. You get the slide and it visually confirms the analyzer data. You see a sea of microcytic, hypochromic cells. You see the normal RDW reflected as a lack of significant anisocytosis. But what specific poikilocytes are you looking for?
The smear is beautiful. You'll see a whole variety of shapes because of that splenic pitting we talked about. But two findings are particularly characteristic. The first is target cells, or codicytes. These look like a bullseye. This happens because the cell has lost so much internal volume from the lack of hemoglobin, but retains its original amount of cell membrane. This excess surface membrane puckers up in the middle, creating the targetoid appearance.
And the second finding?
Basophilic stippling. You'll often see red cells with fine or coarse blue-purple granules scattered throughout the cytoplasm. These granules are aggregates of ribosomes and ribosomal RNA. In normal red cell maturation, the ribosomes are degraded. In thalassemia, the disordered hemoglobin synthesis pathway interferes with this breakdown process, so the ribosomes persist and clump together. Prominent basophilic stippling in a microcytic picture is highly suggestive of either thalassemia or lead poisoning.
So our lab picture is building. Microcytic, hypochromic anemia with a normal RDW, a high RBC count, and a smear showing target cells and basophilic stippling. This is a mountain of evidence pointing away from iron deficiency. But what is the definitive test to rule out IDA?
The iron panel. This is where you prove that iron is not the problem. In an uncomplicated thalassemia trait patient, what do we expect to see? The body has no problem absorbing or storing iron. In fact, due to the ineffective erythropoiesis, iron from destroyed precursors is constantly being recycled, and the anemic state can even signal for increased absorption. So the iron panel will be normal or even elevated.
Let's spell it out. You'll see a normal to high serum iron, a normal to low TIBC. The body isn't desperate for iron, so it's not making extra transferrin. A normal to high transferrin saturation, and most importantly, a normal to high serum ferritin.
Perfect. The CBC and smear give you the suspicion. The iron panel rules out the main mimic. Now, how do we prove it's thalassemia and figure out which type it is?
For that, we need to directly look at the hemoglobin proteins themselves. The gold standard test is hemoglobin electrophoresis, or more commonly now, high-performance liquid chromatography. These techniques separate the different types of hemoglobin based on their electrical charge and size.
As we said, a normal adult has about 97% HbA, alpha-2 beta-2, about 2 to 3% HbA2, alpha-2 delta-2, and less than 1% HbF or fetal hemoglobin, alpha-2 gamma-2. In beta thalassemia trait, the body can't make enough beta chains for HbA. To compensate, it slightly ramps up production of the other non-alpha chains it can pair with the abundant alpha chains.
So it makes more delta chains and more gamma chains. When you run the HPLC, you see a characteristic pattern, a slight decrease in the percentage of HbA and a diagnostic increase in the percentage of HbA2. An HbA2 level above 3.5% is the hallmark laboratory finding that confirms a diagnosis of beta thalassemia trait. You may also see a slight elevation in HbF as well.
So the lab diagnosis is a complete story. CBC suggests a uniform microcytic process. The iron panel rules out iron deficiency, and the HPLC pinpoints the specific compensatory globin chain pattern locking in the diagnosis. Now, that's beta thal. What about alpha thalassemia? It can be a little trickier.
It can, because the genetics are more complex with those 4 alpha genes. Let's run through the possibilities quickly. One deleted alpha gene is a silent carrier. They are hematologically normal. 2 deleted alpha genes gives you alpha thalassemia trait. On the CBC, this looks identical to beta thalassemia trait. Low MCV, high RBC count, normal RDW.
But when you run the HPLC on a patient with alpha thalassemia trait, what do you see?
You see a completely normal result. HbA2 and HbF are not elevated. This is because the problem is with the alpha chains, which are a part of all adult hemoglobins. There's no other chain to upregulate in compensation. So, alpha thalassemia trait is often a diagnosis of exclusion. You have a patient with the classic thalassemic CBC picture, a normal iron panel, and a normal HPLC. The definitive diagnosis requires genetic testing.
Now, what about the more severe alpha thalassemias? If you have 3 alpha genes deleted, you get hemoglobin H disease. This is a serious, lifelong hemolytic anemia. The pathophysiology is the inverse of beta thalassemia. You have a severe shortage of alpha chains and a massive excess of beta chains.
And what do those excess beta chains do? They form tetramers, 4 beta chains bound together, which is an unstable, abnormal hemoglobin called hemoglobin H, HbH. This HbH precipitates in the red cells, causing membrane damage and rapid removal by the spleen.
And this gives us a fantastic, specific lab finding. If you take the blood from a patient with HbH disease and perform a supravital stain, like with brilliant Kressel blue, you will see the precipitated HbH. The red cells are filled with tiny uniform inclusions that give them a stippled appearance, often described as looking like a golf ball or a raspberry. It's a stunningly specific finding. Electrophoresis will also show a fast-moving band corresponding to HbH.
And just to complete the picture, the deletion of all 4 alpha genes results in a condition called hydrops fetalis. With no alpha chains, no functional hemoglobin can be made at all. Fetuses produce an abnormal hemoglobin called hemoglobin Bart's, which is a tetramer of gamma chains, gamma-4. This hemoglobin has an extremely high oxygen affinity and cannot release oxygen to the tissues. The condition is incompatible with life.
A fantastic, comprehensive overview. So let's pull it all together. As an MLS, you see a CBC with a microcytic anemia. Your first thought is IDA. But then you see the RDW is normal and the RBC count is over 5 million. Your brain should immediately pivot. You're no longer thinking supply problem. You're thinking faulty blueprint. You look at the smear and see target cells and basophilic stippling, strengthening your suspicion. You recommend an iron panel, which comes back normal or high, effectively ruling out IDA. The final piece of the puzzle is hemoglobin analysis by HPLC, which can definitively identify beta thalassemia by a high HbA2, or if normal, point you towards a diagnosis of alpha thalassemia.
It's a beautiful cascade of logic, and every step is rooted in the underlying pathophysiology, a quantitative defect in globin chains leading to underhemoglobinized cells, and, in more severe forms, the destructive effects of precipitated unpaired globin chains.
It truly is. We've now covered problems with iron supply in IDA, problems with iron access in ACD, and today problems with the globin protein in thalassemia. We've just about covered the major causes of microcytic anemia, but there's another more fascinating, though rarer culprit to discuss.
You must be thinking of what happens when the iron is there. The globin blueprint is fine, but the factory has a problem with the final step of assembly. The iron can't be properly incorporated into the protoporphyrin ring to make heme.
Exactly. A defect in heme synthesis itself. This leads to a curious situation where iron gets into the mitochondria of the erythroblast, but then gets stuck, piling up around the nucleus. This brings us to our next topic, the sideroblastic anemias.
I love it. We'll explore the mystery of the Prussian blue stain and the iconic ringed sideroblast next. That's a perfect place to leave it for today. Join us next time on The Deep Dive.